Let's now proceed to problem 3. A 534 Newton force is applied to a lever shaft assembly as shown. So this is the lever shaft. Determine the scalar component of the moment at point O about line OB. So let us try to determine the scalar component of the moment at point O about line OB. So first, let us try to determine the coordinates of the different points. So this is now your point A, this is point B. Of course, point O is the origin of the coordinate system. And then we now have your point C. Now, the coordinates of points start with point O, which is the origin of the coordinate system. So we have 0, 0, and 0. Now, for point A, the coordinates of point A is in the x-axis, that is 275 mm, or that is 0.275 meter. And then, and the y-axis, so this is equal to 350 mm, or that is equal to 0.35 meters. And in the z-axis, it is equal to 0. Let's proceed to point B. So we now have your point B. So the coordinates of point B in the x-axis. So your point B in the x-axis is still equal to positive 275 mm, or that is again 0.275 meters. And then in the y-axis, it is equal to 0. And in the z-axis, it is, so we have your z-axis, so that is 150 millimeter, or that is equal to 0.15 meter. So these are now the coordinates of the different points. We still have your point C. So the coordinates of point C. The coordinates of point C in the x-axis is, this is the levers parallel to the x-axis. 325 mm, or that is equal to 0.325 meter. And in the y-axis, it is equal to 0. And in the z-axis, that is equal to 400 millimeter, or 0.4 meter. We now have the coordinates of the different points of the figure shown. Next, let us first express the force F. If you try to express the force F in Cartesian vector form, and the value of the force F is equal to, the magnitude of the force F is equal to 534 Newton. Okay, express this in Cartesian vector form. So to express this in Cartesian vector form, okay, so we now have your F is now equal to the scalar value of F where it says equal to 534 newtons. Multiply this one by a unit vector in the direction of F. So that is from point C to point A. So the unit vector is directed from point C to point A. Now, so we now have your unit vector CA as now equal to a vector distance CA all over the magnitude of this vector distance. Now, let us try to determine now the components of the distance CA. So we now have your x component, we have your y component, and we now have your z component. So the first is directed from point C to point A. So again, this is head minus tail. So it is A minus C. So that is A. So we have 0.275 minus 0.325, or that is equal to negative 0.05. So the y component, so A minus C. So it is 0 minus 0.35. So this is A minus C. So that is 0.35. 0.35 minus 0, or that is equal to 0.35. And we now have your z component. That is again A minus C. So we have 0 minus 0.4. So that is equal to negative 0.4. We now have the components of the distance CA. Hence, the vector distance CA is now equal to xi, which is the x component, minus 0.05 I, and then plus 0.35 j minus 0.4 k. And the magnitude of this vector distance CA is now equal to the square root of x squared. So we have 0.05 squared plus 0.35 squared plus 0.4 squared. And this is equal to the square root of 0.285. Let us now then express your f in Cartesian vector form. So your f therefore is now equal to 534 times a unit vector CA. So we have the vector distance CA is minus 0.5i plus 0.35j minus 0.4k. Let us divide this by the scalar value of this vector distance CA, which is equal to the square root of 0.285. Hence, your vector f in standard Cartesian form is now equal to 534 by 0.05. So this is negative 0.05. all over the square root of 0.285. So we have negative 50.014i plus 534 by 0.35 over the square root of 0.285. So we have 350.096J. And then minus 534 by 0.4 all over the square root of 0.285. We have minus 400.109K. Now, so we are required to determine the scalar component of the moment at point O about line OB. So the moment of the vector F about line OB is now equal to the moment of this vector about point O, as indicated in the problem. So moment about point O dot a unit vector in the direction OB. So we have a unit vector in the direction OB. Now, you try to take note, if you try to recall your dot product, so the component of any vector in any desired direction is equal to the dot product of that vector with a unit vector in that direction. So this is true for moment. Okay, moment about point O. So first, let us try to determine now the moment about point O. So the moment about point O, first, let us try to introduce a position vector. So let us try to introduce a position vector. Introduce a position vector Now, that position vector is directed from O to A. A position vector ROA. To determine your MO, introduce a position vector ROA. Now, you try to take note that we defined before the moment about the point, the moment of vector about the point is equal to the position vector cross the vector itself. And the position vector should be introduced originating from the moment center to any point along its line of action, provided that the coordinates of that point are known. Okay, so this is now the position vector that is from point O to point A. So this originating from point O to point A. So this is therefore the position vector ROA. So how are we going to determine now the position vector ROA? So again, let us try to determine the components of the distance OA. So let's try to determine now the components of the distance OA. Okay, so the position vector originates from point O going to point A, or from the moment center to point A. So we now have your x component we now have your y component and we have your z component. So in this case, we now have a minus o. So that is a minus o. So your a minus o, 0.275. 0.275 minus 0, 0.275. And then we have 0.35 minus 0, that is 0.35. And we now have your z component, 0 minus 0, and that one is now equal to 0. So we are now ready to determine now the position vector ROA. So the position vector ROA is now equal to xi. So we have 0.275i plus yj, that is 0.35j. And your k in here, and your z component is 0. So your k in there is equal to 0. Now, knowing now the position vector from point O to point A, and the vector, we are now ready to determine the moment about point O. So the moment of the vector about O, you try to take note that is also that is the moment center. So the moment of the vector about point O is now equal to the cross product of a position vector and the vector itself. So let us apply now the second order determinant or the third order determinant. So we have your m's of O is now equal to MO is equal to. So your ROA, again, I'm going to repeat that the position vector always comes ahead to that of the vector. So we have 0.275, we have 0.35, and that is equal to 0. We have minus 50.014. This is 350.906 and negative 400.109. We now have your I, we have your J, and we now have your K. So these are orthogonal unit vectors. Let us try to reduce this one into second degree determinants. So we have again your I, remove the row and column of I. So what is left is 0.35. We have 350.906, and then that is 0 and negative 400.109. Plus, we have your J. Again, remove the column and row of J. So we have what's left is 0, negative 400.109. So that is 0.275, and then negative 50.014. 50.014 plus K. So we now have plus K, and then remove again the row and column of K. So we have 0.275, that is minus 50.014. 0.014, and then 0.35, that is 350.906. So let us now evaluate the moment of the vector about point O. So again, this is positive in that direction. So 0.35 by negative 400.109, that is equal to negative 140.038. Okay, so this is minus, that is minus 0, and that one is I. And then we now have plus. We have this one is 0, minus. This one in here is minus. Minus 400.109 by 0.275 is equal to 110.030. 110.030. So we now have your J. Okay, so plus. We have, again, this is positive. So we have positive 0.275 by 350.906. That is 96.276. That is 96.276 minus negative 50 by 0.35. That is equal to 17.505 minus 17.505. And we now have your K. Hence, the moment of the vector about point O is negative 140.038I. Minus and minus is positive, plus 110.030J. So minus and minus is positive, plus 96.276 is plus 113.781K. So this is therefore the moment of the vector about point O. Since we are required to determine, okay, the moment of this vector about point O, okay, of the moment at point O about line OB. So we are now ready to determine the moment about line OB is now your MO dot a unit vector OB. So let us try to determine now this unit vector OB. Now, the unit vector OB is now equal to the vector distance OB all over the magnitude of this vector distance. So first, let us try to determine the components of the distance OB. We have the X component, we now have the Y component, and we now have your Z component. So that is OB, Hence, it is B minus O. B minus O. So, B minus O. So, we have the x component, 0.275 minus 0, 0.275. We have 0 minus 0. 0 minus 0, that is equal to 0. And then we have 0.15 minus 0, so we have 0.15. And therefore, the vector distance OB, or your ROB, is now equal to 0.275I. Y is 0, Z is plus 0.15K. And the magnitude of this vector distance is now equal to the square root of 0.275 square plus 0.15 square. And this is therefore equal to the square root of 0.098125. 0.09815. This is the so the unit vector. We now have the unit vector OB is now equal to 0.275I plus 0.15K all over the square root of 0.098125. And this is therefore, so your NOB is now equal to, or the unit vector in the direction OB is equal to, so 0.275, you divide this by the square root of 0.098125, and that is equal to 0.878I. 0.15 over the square root of 0.098125 is equal to 0.479. 0.479, and that one is K. Let us now determine the moment. Let us now determine the moment of this vector about line OB. And that is equal to the moment of that vector about point O, that a unit vector in the direction of moment. So, your moment about point O is equal to, we have negative 140.038I plus 110 point plus 110.030J plus 113.781.781K. So we now have that a unit vector 0.878I plus 0.479K. And this is therefore equal to minus 140.038 by 0.878. This is negative 122.953. Recall your dot products. The result of the dot product is a scalar quantity. Then we now have your J, so that is we do not have J0 in here. So we have 113.781 by 0.479. That is plus. We have 54.501. And therefore, this is equal to negative 68.452 Newton meter. So the unit of the vector is in Newton, and the unit of the corresponding distances we have in here is in meter. So we converted this distances in meter. So the moment of this vector about line OB is now equal to negative 68.452 Newton meter. Or, to evaluate from scalar triple product. From scalar triple product, so we have your, if you try to recall that vector A dot quantity vector B cross vector C is equal to or quantity vector B cross vector C dot vector A. So that is from scalar triple product. And we evaluate the value of the scalar triple product before. So let us try to apply what we did in evaluating the scalar triple product. So your MOB is now equal to the moment of the vector F about point O dot a unit vector OB. But the moment of the vector F about point O is ROA, so that is the position vector cross the vector itself. So the moment about line OB is now equal to the position vector OA cross vector F dot a unit vector OB. So let's write to your position vector OA is equal to 0.275I plus 0.35J. So that is your position vector OA. Now the vector F is equal to negative 50.014I plus 350.096J plus a minus 400. So we have minus 400.109K. And the unit vector OB is equal to 0 0.878I plus 0.479K. Let's try to evaluate now the moment of the vector about line OB using now your scalar triple product. So we have 0.275, we have 0.35, K is 0. So this is minus 50.014. This is 350.096 and negative 400.109. And then this is 0.878. So J is 0 and your K is 0.479. So it's 0.479. Again, we have 0.275 minus 50.014 and 0.878. And then 0.35, we have 350.096, and this one is equal to 0. That's it. Now, let us try to evaluate now the moment. Okay, so this is therefore equal to, so this is equal to, so this one is 275. So we have positive in here. 0.275 by 350.096 by 0.479 is equal to 46.116. Okay, so that is plus and 0.35 negative 400.109 by 0.876 is plus times a negative is minus 122.953. 0 by negative 50 and 0. So this is equal to 0. So plus 0. Minus. Let's start here. That one is equal to 0. And then next, this one, so that is equal to 0. And this one is negative 0.479 by negative 50.014 by 0.35 is negative 8.385. And this is therefore equal to negative 68.452 Newton meter. So that is the moment about line OB, that is using your scalar triple product. We have problem number 4. Determine the moment of the 950 Newton force about point C. So we are getting the moment of the 950 Newton force about point C. So in this case, we are getting moment about the point. In the previous example, that is sample problem number 3, we're getting moment of a vector about a line or about an axis. So first, let us try to express the 950 Newton force in vector Cartesian form. So let us try to express F in express F in Cartesian vector form. So in Cartesian vector form, this is equal to the magnitude of F, multiply this one by a unit vector in the direction of F, and that is now a unit vector AB. So let us try to determine the coordinates of the different points. Of course, the origin, that is 0, 0, 0. And then we now have your point A. So this is now your point A. So your x-axis is 120 mm, or that is 0.12 meters. So in the y-axis, it is 180 mm, or that is 0.18 meters. And in the z-axis, it is 380 millimeter, that is 0.38 meter. We now have your point B. So your point B in the x-axis, okay, so it's point B in the x-axis is 240 mm, that is 0.24 meters. So the y-axis of point B, so this is the y-axis, so it is 400 millimeter, or that is 0.4 meter. And in the z-axis, so that is 240 mm, or that is equal to 0.24, so 0.24 meter. So point C, that is now your point C. Now the x-axis, so this is your point C. So the x-axis is 180 mm. It is back of the origin, so we have negative 0.18 meters, 0.18 meter. C and the y, your y is 270 mm, so that is 0.27 meter. And your z in the z is equal to 0. So these are now the coordinates of the different points. So let us try to determine now a unit vector AB. And this is equal to a vector distance AB all over the magnitude of this distance, vector distance. So, components of the distance AB, so we have the x, your y, and your z. So it is b minus a. So b minus a, so 0.24 minus 0.12, and that is equal to 0.12. 0.4 minus 0.18 minus 0.18, and that one is equal to 0.22. And then 0.24 minus 0.38 is negative 0.14. So that the vector distance AB is now equal to xi 0.12i plus yj 0.22j plus zk minus 0.14k, and its corresponding magnitude is now equal to the square root of 0.12 square plus 0.22 square minus 0.14 square. And this is equal to the square root of 0.0824. 0.0824. Okay, knowing now the vector distance AB and its corresponding scalar value, we're now ready to determine the unit vector AB. Hence, your F is now equal to, so your F is now equal to 950 multiply this one by 0.12i plus 0.22j minus 0.14k over the square root of 0.0824. So, in Cartesian vector form, this is equal to 950 by 0.12 over the square root in here is 397.138i plus 950 by 0.22 over the square root of 0.0824, 728.086, 728.086j minus 950 by 0.14 over the square root of 0.0824, that is equal to minus 463.327. So that is 463.327K. Let us now determine the moment of this force about point C. So the moment of this force about point C is again, now let us try to introduce a position vector originating from the moment center. And our moment center is point C to any point along its line of action, provided we know the coordinates of that point. So I'm just going to consider a position vector CA. So this is now the position vector CA, and that is RCA. So we introduce a position vector RCA. That is the position vector RCA. So, let us try to determine the components of the distance CA. We have your X, we have your Y, and your Z. So this position vector is from point C to point A. So again, head minus tail. So A minus C. So point 12, minus and minus. So we have 0.12 minus and minus 0.18. And this is equal to 0.3. Then 0.18 minus CA, 0.18 minus 0.27. So that is equal to negative 0.09. And then 0.38 minus 0, and this is equal to 0.38. Hence, the position vector RCA is now equal to 0.3i minus 0.09j plus 0.38k. So the moment of the vector about point C, so it's the moment center, because the position vector always originates from the moment center, is now equal to the position vector CA cross the vector itself. Is cross the vector itself. So we now have the moment about point C is now equal to, again, the position vector 0.3 minus 0.09 and then 0.38. Now, we have the vector F as 397.138 we have 728.086 and minus 463.327 463.327. So we now have your I, this is your J, and that is now your K. So we now have, let's try to reduce this one, the second order determinant, minus 0.09 and 728.086. 0.38, and that is 463.327. Okay, plus J, this is 0.38. We have 463.327. That is 0.3 This is 397.138. And then plus your K. So we have 0.3. That is 397.138. Negative 0.09. This is 728.086. Now, let's try to evaluate now the cross product of the position vector CA and the vector itself. Okay. Minus 0.09 by 463 is so this is negative. So we have negative. This one in here is negative 463. Minus 0.09 minus times negative, that is positive. So there's one in here. So we have positive 41.699 minus 728.086 by 0.38, and that is equal to 276.673 I. Okay, plus, so that is positive 0.38 by 397.138. That is equal to 150.912. 912 minus, so this is minus negative 463.327 by 0.3 is negative 138.998. 138.998. And then J plus, this is positive 0.3 by 728.086. That is 218.426 minus, so we have 397.138 by negative 0.09 is negative 35.742. 0.742. And this is now your K. And the moment, therefore, of the vector about point C is minus 234.974 I plus, we have 289.91 J, and then plus 254.168 K. So this is now the moment of the vector F about point C. You try to take note that when you introduce a position vector, that position vector always originates from the moment center to any point along its line of action. But be sure that that point along its line of action, the coordinates must be known. Okay, problem number 5. If F1 is equal to 100i minus 120J plus 75K, and F2 is minus 200I plus 250J plus 100K in pounds. Determine the resultant moment produced by these forces about point O, and express the result in Cartesian vector form. So, again, let us try to determine the moment of the two forces about point O. And the moment of the two forces about point O is now the moment of F1 about point O plus the moment of F2 about point O. So how are we going to determine the moment of F1 about point O and the moment of F2 about point O? Okay, first, we have the coordinates of the 2 points. We have the origin is, of course, 0, 0, and 0. Again, this is your x, y, and z axis. And then for point A, your x is 4 feet. And then your y is 5 feet. And your z is 3 feet. So let's try to determine the moment of the two forces about point O. Again, let us try to introduce a position vector originating from the moment center to any point along their line of actions, provided that we know again the coordinates of that point. So again, this is again the position vector ROA. So originating from the moment center. So that is your ROA. So let us try to determine the position vector ROA. So in here, we introduce a position vector ROA. So we now have the components of the distance OA. So that is A minus O. We have your X, we have your Y, and we have your Z component. Now, your 4 minus, that is equal to 4, then 5 minus 0, 5, and then 3 minus 0, that is equal to 3. That one is equal to 3. Now, your position vector OA 4 is now equal to 4i plus yj plus zk. So that is the position vector. Let us try to determine now, first, the moment of F1 about point O is now equal to ROA cross the vector F1. ROA cross the vector F1. So we now have your ROA, your F1 in here is equal to 100I minus 120J plus 75K. So we now have the components of F1. So we have your Fx is equal to 100 pounds. Your Fy is equal to negative 120 pounds. And your Fz is equal to 75 pounds. So, the moment of F1 about point O is now equal to, so we have your ROA, so that is now your 4, 5, and this is 3. So we have 100, negative 120, that is 75. So we have your I, J, and that is now your K. And this is equal to I. Then we have 5, negative 120. That is 3 and 75. Plus J. So we have 3, 75, 4, and 100. So we have plus K. We have 4, 100, then 5, negative 120. And this is therefore equal to 5 by 75 is equal to, so let's try to get now, your I is 300, 5 by 75, so that is 375, minus negative 120 by 3 is minus 360, minus 360. We now have your I. Plus 3 by 100 is equal to 300. Minus 4 by 75 is 300. And that is now your J. And then we have plus. So we have 4 by negative 20 plus, so that is negative 480. That is minus 480. Minus 100 by 5. So that is minus 500K. And therefore, the moment of F1 about point O is equal to 735I okay, 0 sa J, and then minus 980 K. So that is the moment of F1 about point O. Di mo makitan. Charles. Ay, nagkasamit 10. Ako ang samit 10. Nagkasaksamit 10. Okay, let us try to determine now the moment of F2 about point O. And still, the position vector introduced is position vector OA. So that is ROA cross F2. So we have the components of F2. So this is F2. So your Fx is negative 200 pounds. Your Fy is equal to positive 250 pounds, and your Fj is equal to 100 pounds. Hence, the moment of F2 about point O is now equal to, so we have now the cross product of the position vector and the vector F2. So that is again 4, this is 5, and this one is 3. So we have 200, negative 200, we have 250, 100, this is your I, we have your J, and that is now your K. So this is equal to, again, I. So we have 4 minus 200. That is 5. That is 250. Okay, so plus. We now have your J. So we have 3. And then, so your I is... eliminate the column of I and the row of I. So your I is 5 and 2, 250. So that is 5. And then we have 3 and 100. Okay, plus J. So we have 3, 100. We have 4, negative 200 plus K. So we have 4 minus 200, 5, and that is 250. So the moment of F2 about point O is now equal to 5 by 100 is 5 by 100 is equal to 500. Minus 250 by 3 is 750. So we have your I. Plus 4 by 100, 3 by minus 200 is minus 600. Minus 4 by 100 is 400. And this is now your J. Plus 4 by 250, that is equal to 1,000. Minus, so we have 5 by negative 200 is minus 4 by 250 is equal to 1,000. And then, this 1,000 minus and minus 1,000. And that is now your K. So this is therefore equal to, so that is negative 250i minus 1,000j. Minus and minus is positive, so we have plus 2,000k. That is plus 2,000k. Now, let us try to determine now the moment of the two forces about point O. So your MOF1 is 735I minus 980K plus the moment of F2 about point O is minus 250I minus 1,000J plus 2,000K. So the moment of the two forces about point O, 735I minus 250I is equal to 735 of I, and then we have 250 of I, so that is equal to 485. So it is 485I. So J minus 1,000J. So minus 980K plus 2,000K. This is equal to 1020K. So that is plus 1020K. So this is in pound-foot or foot-pounds. The unit of the force is in pound and the unit of the distances is in feet. So this is foot-pounds. So if you try to determine the scalar value of this moment about point O, so the scalar magnitude is equal to the square root. So we now have the scalar value of this is now equal to the square root of 485 square plus 1,000 square plus 1020 square. So that is equal to 1508. So we have 1508.571 foot-pounds. So that is the scalar value of the moment of the two forces, F1 and F2, about point O. Ini nagkastama din kapit kasi nas dyan natin. Diyan kami makita. Okay. Dito yung manin. Ni apa sublino i-stop ko. DJ nga yun, alam.